All right, so we've got a little warm up this time, which is unusual for us. Here we've got a current flowing counterclockwise in this wire, and what I'd like you to do is try to use your right hand rule, put your thumb along with that current, and tell me for this loop, what does the magnetic field look like everywhere inside the loop and everywhere outside the loop? Well, we'll reveal the answer to that in just a moment. Today, we're going to be tackling one of our last play posits of the year, and we're going to be attempting to describe the direction and magnitude of what's called induced EMF and induced current. EMF is that little curly E, and it's, again, when you see EMF, don't worry, it's the same as voltage. So we're going to try to describe the direction and magnitude of these induced currents and induced voltages using Faraday's and Lenz's law. So we're going to do a little reminder of a right-hand rule, talk about what the heck we're talking about anyway, how to calculate magnetic flux, and then close out with Faraday's and Lenz's laws. But first, let's talk about our little warm-up here. So if you follow the right-hand rule here and you put your thumb along with the current, because this was the way we did it for a wire, your thumb goes with the current, excuse me, not with the B field, your thumb goes with the current. And the curl of your fingers tells you the B field. What you can find is that, let's see, I do it up here and I get into the page and out of the page. Over here, okay, my thumb goes down and I get into the page, out of the page. Here I get, okay, thumb goes this way, I get out of the page here and into the page here. Oh, look, everywhere I go on this, I get out of the page on the inside and into the page on the outside. And here's a little 3D GIF of it. And you'll notice that it kind of draws those little loops for us, but also draws that the direction of the B field in the middle of the loop is out of the page. We actually, as it turns out, for loops like this and solenoids, which are basically, if you remember from the last video, solenoids are just loops upon loops, big coils of wire. We actually have a new version of the right-hand rule we can use to figure out the direction of the field, which is that instead we curl our fingers in the direction of the current. So I want you to try this with our example. If you curl your fingers in the direction of the current, then your thumb points out of the page and tells you the direction of the magnetic field in the middle. So we actually have two versions of the right-hand rule that we can use here. For straight wires, we can make sense of this by looking at it as a wire and using our traditional one. We can also use this new rule for a loop and figure out the direction of the magnetic field that way. If this new version scares you, don't worry too much. You can still use the original right-hand rule. So we actually now have four things we can do with our right hand. If we want to find the magnetic field, we now have two options. For a straight wire, we can point our thumb in the direction of the current and our fingers curl in the direction of the magnetic field. If instead we have a loop, we can instead curl our fingers in the direction of the current, and our thumb now tells us the direction of the magnetic field. It also specifically points in the North Pole direction. And the way that I keep these things straight in my head is I remember that my thumb is like more or less straight. It points in a direction. And so I point my thumb in the direction of whatever is going in a straight line. So over here, my thumb is going with the current because the current is in a straight line and the magnetic field is circulating. Over here, my thumb goes with the magnetic field because the magnetic field is more or less in a straight line, at least in the middle, and the current is circulating. So if we want to find our magnetic field, we have two options here. If instead we already know our magnetic field, we can use those things that we did in class on Monday and use our cross product to figure out those forces. So if you remember from class on Monday, we had that QV cross B option. We also had that Li cross B option for wires. So we actually have four things we can do with our right hand. And I just want to pause for a moment and say that these four things you can do with your right hand are really super important. And if you want to do well in magnetism, if you really want to understand magnetism, understanding what you're doing with your right hand at any given time, or I guess if you have a negative charge, your left hand, but understanding these applications of the right hand rule really well is super important. So I would think hard about them. Think hard about, am I trying to find a field or am I trying to find what a field is going to do in that case. So keep those in your head. So Michael Faraday, this famous scientist, discovered something really peculiar in 1831, which is that if you put a magnet into a loop of wire, you suddenly get current in the wire. You don't have to touch the magnet in. You just have to wave it around, put it inside the loop of wire, and you get magically current. So here's an example of this little thing that we've got set up here. I've got my bar magnet, and it is going through a little loop of wire. You'll notice I'm not getting any voltage right now, but if I start to move my magnet, I get voltage and therefore current flowing in my wire. If I move it quickly, I get a lot of voltage and a lot of current. If I move it slowly, I get just a little bit. If I don't move it at all, if I put it inside and leave it there, I get nothing. So I only get that voltage, I only get that current while my magnet is moving. You'll also notice as I put the north end in, my voltage goes negative, then positive on the way out. If I go back the other way, I get negative, then positive on the way back out. So clearly something interesting is happening here, and it only happens when I'm moving. This is part of a really useful and interesting mirror in electromagnetism. We already know that current, which is moving charge, can generate a magnetic field. What this implies also, which is really interesting, is that a moving magnetic field can generate current. So we have this mirror image that if I'm moving charges around, if I have my current flowing, I generate a magnetic field. If I start moving a magnet around, if I start changing my magnetic field, I can get an induced current. And that's what we call it. When you move this magnet in and you get that little current in here, we call that the induced current. Because just like induced charge back in the day, we are making that charge out of nothing. Similarly, you can get that momentary current through another electromagnet. We'll take a look at something like that later. The reason you get this induced current is because of something called motional EMF. So let's say I start waving a metal bar around in a magnetic field like you do. And imagine that you are one of those lonely little positive charges sitting inside this bar of metal. And, you don't have to remind me, Mr. Bates, positive charges don't move. I know they don't move. But when people were thinking about this back in the day, they didn't know that. So it's all stated in terms of positive charges. But if you're this lonely little positive charge and suddenly you're moving, well, all of a sudden, because the bar of metal you're in is moving, you're now moving through a magnetic field. And as we discovered in class the other day, if you move across a magnetic field, you suddenly feel a force. So let's see, I can use my right-hand rule. My velocity is to the right. My magnetic field is into the page. If I use my right-hand rule, I get a force, indeed, up the page. So charges moving relative to a magnetic field, we know this, they feel a force. So my charge gets pushed up the page. And so what happens is, I guess if positive charges go up the page, you might logically expect, you would be correct, that negative charges should move down the page. So you get this charge separation, positives to the top, negatives to the bottom, haters to the left. As it moves more and more through the field, you'll get a greater and greater charge separation built up until you can't push any more charge. Positives don't want to go up anymore because there's too many positives. And what you get here is you get a voltage difference across your metal bar. You get this EMF. There's an electromotive force, which is what EMF stands for. You get a voltage that has separated these charges. And if you have a long enough wire, you actually get a current. So movement through a B field causes a voltage. In order to figure out why and in what direction and how much, we've got to go back and rely on flux. So a quick little reminder of how we calculate flux. We used to do this for electric fields, now we're doing it for magnetic fields. So as a reminder, if your field is perfectly perpendicular everywhere to your loop, it's just going to be, well, your flux here would be just B times A times your area. In this case, if it's at a little bit of an angle, it's going to be B times A times the cosine of the angle. And let's just be careful. The angle is actually measured between the field and this little normal vector. from your surface. And if it's perfectly parallel everywhere, your flux is, of course, 0. And again, if it's at an angle, you got to take that into account. Only the component pushing through your surface counts. What is our unit of flux? Well, it's Tesla times area, B times A. But we actually have a special name for that. It's called Weber. And we write Webers this way. 1 Weber has a WB. And the reason is we don't write it this way is that's 1 watt. Exactly. So let's take a look here. Here's a little example. We've got a 10 centimeter circular loop. They give us a side view, so I'll draw you a better view. And they give us the field strength, and they want us to calculate the flux through the loop. All right. Well, what we had to do here is a couple obnoxious things. This is almost like a UT Quest question. We had to recognize that our radius is not, in fact, 10. Our radius is 5, or I guess 0.05 in meters. We also have to recognize that our flux here is not all perfectly perpendicular to our surface. So we are going to get B times A. Let's see, that's going to be pi r squared, because it's a circle, and I know that. And in this case, I got to figure out, okay, what is our component this way? What is our component this way? Well, let's see. I could use the sine of 30, but instead I'm going to use this angle, which is actually going to be, in this case, 60 degrees. And so I'm going to use in here the cosine of 60 degrees, which I happen to know is 1/2. And if I go ahead and calculate all that, 0.05 times 0.05 squared times pi times 1/2, I'm going to get 1.9 or so times 10 to the -4th watt. No, not watt, Weber. Very good. Okay, so we will do an example of this in class, but just in case we get a non-constant magnetic field, sometimes we will have to do an integral. So we will deal with one of those in class. All right. Lenz's law, though, we still got to figure out, now that we've got flux under our belt, we can kind of come to this thing, Lenz's law. Lenz was a different guy, not Faraday. Lenz's law states that there is an induced current. You get an induced current in a closed loop if and only if the magnetic flux is changing. Is our flux changing? If our flux is changing, we will get an induced current. And the induced current takes on a direction to try and fight the change in flux. So the idea is that if my flux is increasing, I'm going to get an induced current that's going to try to decrease my flux. If my flux is decreasing, I'm going to get an induced current that's going to try to increase my flux. It is always going to fight me. So you can kind of see here as I move my magnet around, right? Think about the number of field lines that are going through my little loops here. As I move my field in and out, I'm changing the amount of my magnetic field that's being captured. I'm changing my flux, and that's why I get a current. So I got to figure out which way my change is going. So here's what I'm going to do. In all my cases, I'm going to find the direction of my flux. I'm going to find the direction of change. I'm going to point my thumb in the opposing direction to fight that change, and then my curled fingers will show me the induced I. So let's try that. Here's in a case where we've got a little loop of wire, and our magnetic field is up and steady. That means it's not changing with time. All right, well, the direction of my flux is upward because that's the direction of my magnetic field. But what about my change? What about my change? In this case, if B is not changing, my flux is not changing. And if my flux is not changing, Lenz's law tells me no change in flux, no induced field, no induced current. Nothing happens. My loop is happy. No induced field, nothing happens. What if instead we have our B field up, but now we try to make it stronger. We crank up our magnet and we try to push more magnetic field through our little loop. Our magnetic field gets stronger. Well, in this case, our flux is still upward, and our change in flux is also upward because it's getting stronger in the upward direction. So what Lenz's law says is that we try to fight that. So my loop is going to try to make a magnetic field that points downward to fight that change. Well, if I put my thumb downward, then my right hand is forced to circulate in a clockwise direction, like that. So what I get is an upward change in flux. So my induced field is going to try to be downward to fight that change. It wants to keep the status quo. It doesn't want my flux to change. So if my flux is changing up, my induced field is down, which requires a clockwise current. B is up and decreasing. So now my magnet is getting weaker over time. Well, my flux is still in the upward direction, but now my change in flux, if it's upward and getting weaker, my change in flux is downward. Lenz's law says, no, you cannot reduce the flux. I'm going to put my thumb straight up, and I'm going to fight that. And if my thumb goes up, then what does my current have to do? I have to get an induced current that is counterclockwise, because my change in flux is down, my induced field is up, which requires a counterclockwise current. So we're really using here that loop version of the right-hand rule that we had before, right? If I have a counterclockwise current, I'm going to get a field pointing up. So my current is trying to fight my change. All right, let's try this one. So now instead of our field being up, my field is being down. In this case, down and steady. So tell me, what current do you think we're going to get here? If you said no induced current, you were correct. It's still steady. Nothing is changing. In this case, it is down and decreasing. So let's see, our flux is down. But if it's decreasing, let's see, if it's decreasing, then down and increasing, I misread, I can't read. Then my change is down because it's getting more and more in the downward direction. So therefore, I need an induced field in the upward direction, which requires a counterclockwise current. And last but not least, down and decreasing. My direction of flux is down, but my change in flux is up. Therefore, my induced field is down, and my induced current is clockwise. So in all cases, this induced current is going to try to fight change. So figure out which way our change is happening, and then you fight it. Once we've figured out the direction, you might logically ask, how do we figure out the number? What is this voltage that gets induced? Faraday's law is the counterpart to Lenz's law, and it tells us that the voltage, the literal number of volts that get applied to our loop, the induced voltage, is exactly equal to the derivative of magnetic flux. So I just want to point out, it is exactly numerically equal to the derivative of magnetic flux. So if I can figure out what my flux is and take a derivative, then I can figure out what my voltage is. And the direction of the EMF is given to us by Lenz's law. All right, let's take an example of this. So this is kind of like a railgun. So what I'm going to do here is I've got a little metal rail. It's a metal rail that has a certain length L. And in fact, L is also the size of this outer loop. That metal rail is attached to some copper piping or copper wiring that kind of makes this little like sideways U shape. And I'm going to put my my metal bar some distance X away from the side. So it cuts off a little box. And what I'm going to do is it actually becomes important that my bar has some electrical resistance R. And what I'm going to do is I'm going to give it a push. I'm going to push it at some velocity v to the right. And what it turns out is that as I'm pushing it, I get some induced current. So let's think a little bit about this. If I look at my box here, if I look at this area in here, I can figure out the flux through that yellow area. Well, in this case, my magnetic field is nice and constant and points just into the page everywhere. So I can just be, okay, my flux is magnetic field times area. Which is going to be, let's see, that's a rectangle. I know how to do rectangles. It's B times L times X. So my magnetic flux is just B times L times X. As my bar moves to the right, though, X is changing, and if X is changing, so is my flux. So let's try to take a derivative, because this is going to give me my voltage, my EMF. All right, well, my magnetic field's not changing, so that's a constant. My length, L, isn't changing, but X is. So I can take a derivative of that. Well, if only we had another word for the derivative of position. Oh, wait, I do. Velocity. So it turns out that the faster my bar goes, the more and more EMF I get, the more and more voltage I get. Let's see, which way is this going to go? Well, my flux is currently into the page. And as my bar moves to the right, my area gets bigger and bigger and bigger. So my flux is increasing. So the direction of change is also into the page. It's getting bigger and bigger and bigger into the page. So I need an induced EMF that will give me a magnetic field. I need to get my induced field to fight that change out of the page. And if I put my thumb out of the page, I end up with an induced current, which they've helpfully drawn for me in that counterclockwise direction. Isn't that lovely? What is that current? Well, if my bar has some resistance R, and that's the only thing in my circuit, I can figure out my current as delta V over R. I guess I should really write EMF over R. And in that case, I can just do this. This is BLV over R. So that's my current. Now, what's kind of funny is this might have occurred to you, maybe not. We now suddenly have a current running through this bar, and it's moving through a magnetic field. So you might say, Mr. Bates, you told us that wires that are carrying current experience forces in magnetic fields, and they specifically experience a force equal to their length times the current through them times the magnetic field. So I can calculate that. Well, I know what I is, and I know what L and B are. So it's going to be B squared L squared V over R. And then what's the direction of that? Okay, well, I've got my current going up the page, my magnetic field going into the page, and if I do my right-hand rule, the direction of that force is to the left. Notice how the force that I'm getting, so this force comes from a really complicated place. This is the force that is the interaction of my induced current with my existing magnetic field. And what you'll notice is that that force opposes my velocity. How would this manifest in real life? Well, if I grabbed my bar and tried to push it to the right, my magnetic field and all this induced current and everything is going to try to push it back to the left. It's going to feel like drag. It's going to feel like moving this bar through honey. I'm actually going to kind of feel the magnetic field. And so in this case, you'll often find this, which is that not only do we get induced currents that try to fight the change in flux, but specifically we get forces as a result of that oppose changes in motion. So if I want to speed this bar up, it'll stop me. If I want to slow this bar down, it will also try to stop me from doing that. So it's a really interesting phenomenon. But we can go ahead and calculate pretty much all the things we want. All right. This has a lot of applications in real life, which we can talk about a little more in class. Transformers, that if I start changing the current through one side, if I have some alternating current going through one side, that it can induce a current in a separate little loop. With a metal detector, if I wave a magnet over some metal, it'll induce currents in that metal, which I can then pick up those kind of the induced magnetic field from it, so it'll get a response from the metal. And there's also this thing called eddy currents, and we'll do a really cool demonstration of this in class, where if you try to put a piece of metal through a magnet, it will actually slow down. And you can actually design electromagnetic brakes. So you can imagine having the rim of a wheel, and when you want to stop, instead of putting on brake pads, you could suddenly turn on a magnetic field across that. You're going to get an induced current all of a sudden in the metal, which is going to act as a drag force and slow your wheel down. So there's some cool demonstrations and stuff we can do in class. All right, with that in mind, I just want to conclude with this idea of electromagnetic induction, that we can use Lenz's law to determine the direction of the induced current. And that direction is always going to be to fight our change in flux. So if our flux is increasing, we're going to get a current that's going to try to decrease it. If our flux is decreasing, we're going to get an induced current, induced field that's going to try to increase our flux again. And the magnitude of that induced voltage, that induced EMF, is exactly equal to the derivative of flux. All right. I will see you later. Thank you very much.